Hi everyone, glad to be here and glad to that you all are here and that we can meet tonight and chat about eBPF. I'm Anna. I work at Isovalent, recently acquired by Cisco, but I don't think I must repeat it every time. So yeah, I work at Isovalent on observability tooling for networking and security use cases. So Isovalent uses eBPF very heavily for networking and security. I work on observability products on top of that. And I'm responsible for making sure that these projects integrate well with the whole observability and Kubernetes ecosystem, which is so big these days. Today I'm going to talk about Tetragon. So Tetragon is the main project I am focused on at the moment. It's an observability and security tool using eBPF, of course, and focus on the cloud-native Kubernetes ecosystem. So without further ado, does it work? Oh, yeah. Tetragon. Tetragon is an open source tool. It's part of CNCF as part of a subproject of Cilium. And it is using eBPF mainly for generating events. The events are low-level events attached to a process. So it's monitoring processes essentially. And it does filtering, aggregation, and also enforcement for security in kernel. It is Kubernetes-native in a way that all events and all data produced by Tetragon has Kubernetes metadata about user workloads, so things like namespaces, workloads, spot names, things like this. And Tetragon is configurable via Kubernetes custom resources. Tetragon is a pretty generic tool, and at first it was developed like a few years ago as part of Isovalent Enterprise Platform. Now, Isovalent Enterprise Platform still uses Tetragon, like the open source project, and kind of builds on top of it. Because Tetragon is so generic, you will see examples in the next slides. There are many things you can build with it. You can use it for observability and security, like just as a tool you install. But we see more and more projects, that more and more people actually building some projects on top of Tetragon. And we essentially do it too at Isovalent. We built a platform that uses Tetragon and adds some advanced features to it. By advanced features, I mean mostly in-kernel network parsers for all popular protocols, both layer 4 and layer 7, so TCP, UDP, HTTP, DNS, and also file integrity monitoring. We also, in the platform, we also try to provide users this sort of out-of-the-box experience. So experience where you install Tetragon, install the whole platform, and you have security and visibility for your needs, for example, your compliance requirements. So we provide default security rule set. We provide UI in the form of dashboards mostly, and integrations with various CMs and popular observability tools. If you want to learn more about it, then feel free to visit the website. All right. So this is a picture that I took it from the front page of Tetragon documentation. There is a lot of going on here, so I will kind of dive into it and into different parts. So first, Tetragon is very generic tool. I'm saying it for the 5th time now, I think. It is, at its core, it hooks into kernel events and produces events, monitors what happens in the kernel. But it can hook into practically any kernel event. And because of that, it can be used for many, many, many different use cases. Some of the most popular ones are process execution and also syscalls. This is the core functionality of Tetragon, because all of the events have this process context, like there's some process running and everything is attached to this process. Network activity, network connections, and network traffic, disk and file access, and some Linux-specific security things like changes in Linux namespaces and capabilities, which are source of some common popular, I mean, some known CVEs that were like very covered by media in the recent years. All right. Then we have eBPF. So I'm not gonna dive into eBPF very, very deeply in this talk. I will mostly talk about how we use it and our experience, our learnings on the way. But something I wanted to highlight is why Tetragon even uses eBPF. The major thing is that, Tetragon is originally developed by kernel developers by BPF maintainers. But what are we getting from using eBPF? We are getting reliability. And this is something I feel is a bit underappreciated when we talk about eBPF, especially in observability context, because many people appreciate that eBPF provides observability with no instrumentation, or that it provides observability with very low overhead. And this is great. This is absolutely great. But this reliability aspect is not really appreciated that much, and it should be, in my opinion, because many of us experienced some dreadful incidents that, for example, affected some sidecars that were collecting telemetry, or many of us have installed some tools that were supposed to provide us observability, and these tools started crashing, and this also affecting the applications running in the nodes. This is awful, and eBPF doesn't completely solve this problem, but because eBPF programs are verified by eBPF verifier, they are safe to run, and they are more reliable than most software we write. They are not bug-free, no magic there, but they are pretty reliable. They provide complete visibility. This is especially important in the context of security observability, because security teams don't like when you tell them that, oh, by the way, we might randomly miss some events. No, they don't want to hear this. They want to have complete visibility, to be sure that you don't miss anything, and we can achieve this more reliably with eBPF. And doing in-kernel enforcement, this was tricky, but this is also a very, very powerful thing, because doing enforcement in kernel means that we are essentially more secure. We are protecting against much wider range of attacks, because we don't have to trust user memory, and this is very, very powerful. eBPF provides us with low overhead. This is a matter of thing for Tetragon. We are trying to develop it in a way that it keep the overhead to the minimum. So BPF programs are generally fast, and major thing that allows us to achieve this low overhead is that we run it in kernel. We don't have to switch back and forth between kernel and user memory. And we also do both filtering and aggregation in kernel, so we can kind of process this data very, very efficiently. We don't have to send it over and over through a few services to kind of filter and aggregate it, as we would do with some other tools. Next thing, the agent. So Tetragon has the BPF part in kernel and agent in user space. The agent can run on any Linux, and it can run in Kubernetes here I will focus on the Kubernetes part, but it can also run on bare metal. It can run as a container or just as a binary managed by systemd or whatever. It can run on any Linux, essentially. The difference is in how you configure it, because when running outside of Kubernetes, of course, you don't have access to all these Kubernetes custom resources, etc. Tetragon monitors user applications, and user applications can be written in any language, can use any framework. Tetragon will see them. This is not to say that eBPF doesn't care about the programming language that application is written in at all. It depends on what you are doing. Sometimes it is relevant, sometimes it is not, but the eBPF programs will see what the application is doing, no matter what language it's written in. And many or most Tetragon use cases are really language agnostic. To monitor applications, we don't have to make any changes to their code or to their configuration, of course. And we also don't have to even restart them or install anything alongside applications like any sidecar or anything like this. The applications just keep running like they were running forever. When we install Tetragon, then Tetragon will just see them without affecting them in any way. And the last bit, integrations and data pipelines. So Tetragon is very low-level tool which generates events in the kernel. And what then? This is a part that, this is essentially my job. This is what I'm focusing on, integrations with the all very big observability and security ecosystem. So Tetragon events can be forwarded to any security, any CM system, like Splunk and Elastic are, I think, some of the most popular ones. Any observability tool that collects metrics or logs. In Kubernetes world, this is usually Prometheus, Grafana, and recently more and more OpenTelemetry. And what many organizations choose to do is to actually build something on their own, to forward the Tetragon events, for example, to AWS S3 or to ClickHouse, and build some queries, some visualizations using this storage. We also developed a tool based on ClickHouse internally to efficiently query these events. All these integrations vary in maturity stages, but you can do whatever. There are a million ways to do it, really. All right, now I wanted to talk a bit about what we learned during the whole process. So Tetragon has a few years, and we've been running it with our customers on pretty large scale already, with a very high compliance environments. And we learned a lot of lessons by working closely with our customers on these production deployments. The first thing is that in-kernel state is powerful for context and avoiding races. And this is a core component of Tetragon are, of course, the BPF programs. And BPF programs use BPF maps for the state, essentially. So we have a few kinds of BPF maps. All of them are essentially some kinds of key value stored in kernel memory. There are many different kinds of BPF maps in general. In BPF, we are using them for a few main things. We store all the processes that we saw we call it exec map. Then we saw sockets that were open in a socket map. Then we have Masa maps for files and for Kubernetes metadata. The Kubernetes metadata part is what is really powerful. because we get this Kubernetes metadata from, we get it from container runtime actually. I won't dive into it, but yeah, we could get it from Kubernetes API, but for security reasons, we switched to retrieve it from container runtimes. Anyway, my point is that we get this Kubernetes metadata in user space. We write it from user space to the BPF map. And then when we are processing events in kernel, we don't have to reach back to user space anymore for this Kubernetes metadata. We just read it from the map. Similar thing applies for processes or sockets that were started before Tetragon started. We can retrieve them and just store them in a map. The next thing is that internal filtering and aggregation are really essential for low overhead. And how observability pipelines usually work is that we collect lots of events, lots of metrics, and then we always somehow filter and aggregate them. It happens at various stages, and sometimes there are many tools involved, but often we are just sending lots of data between many different services to do this. Doing all of this not only in one service, but just in kernel memory is really powerful and allows us to provide this low overhead. So yeah, when we benchmarked the initial versions of Tetragon with customers, that we found that we found some common biggest performance issues, which was completely unsurprisingly the volume of data, because Tetragon can observe so many things. It is very easy to just produce some insane amount of data. But when developing some filters and aggregating data, we could actually make Tetragon very efficient. So yeah, here are some benchmarks. We are benchmarking Tetragon, let's say, semi-regularly. If you are interested in numbers, you can read the blog post announcing the Tetragon 1.0 release. There are some detailed benchmarks that I showed here about the overhead of Tetragon. We are generally trying to keep the overhead 2, 3, up to 5%. This is what seems really good and compared to alternatives. A kernel is more than syscalls. So when eBPF is introduced to people, often it is associated with syscalls, that eBPF programs are attached to syscalls and to something. And yeah, of course, eBPF programs can be attached to syscalls, but they can be attached to many different things. And many Tetragon use cases actually don't attach to syscalls for various reasons, but attach to some underlying kernel function, to kprobes. And this being that generic and digging deeper into the kernel, attaching to kprobes, not syscalls, is what allowed us to serve so many use cases and also provide such a reliable experience. Threat models include bots, containers, apps. Okay, so now I'm gonna dive a little bit into the security part of Tetragon, because Tetragon does observability and security. Observability mostly in the security context, and there are a few things that are very popular in observability tools using eBPF that we chose not to do. We chose not to do them because Tetragon is a security tool in the first place, and these things are not secure and as we would like to. And this includes uprobes. So uprobes are great. Uprobes uprobes allow you to attach BPF programs to user space functions. And this is great in observability tools because like the user observability tools are mostly interested in user functions, right? When you want to observe your application, you want to observe what functions in your code do, not what some obscure kprobes do. And uprobes are great for observability, but from the security perspective, they are problematic because they are in user memory. You have to trust the user to not manipulate them. And when we are building security tool, we don't trust user space. We are assuming that user space might be compromised and controlled by an attacker. Syscall user pointers. This is a similar situation. We actually, for many use cases where we could use syscalls, we don't use syscall, but we use some kernel functions that is like under the hood called by the syscall for this reason that we don't want to compromise user memory. We assume it might be controlled by an attacker. And yeah, the one major thing we learned is that the difficult part of eBPF is really finding where to attach. Because we can attach to anything, but often finding the right function that will work reliably on many Linux distributions and that will provide us data we need is really the difficult part that requires kernel expertise. Next thing is enforcement in kernel on top of visibility. So as I mentioned, Tetragon provides enforcement in addition to visibility. There are a few ways that we do security with Tetragon. The first kind of most obvious and the easiest thing is audit. So we collect a lot of events and then store them somewhere, and then security teams can query them for audit. So query some if everything was right. There's alerting. So alerting is a more synchronous way of doing security, where when we detect something that is suspicious, and we, for example, some known CV being executed, and we alert user, and the user can immediately look into it and mitigate the security vulnerability. The thing is that this user action happens when the attacks might have already been successful. And the sort of next stage is enforcement, where we solve this problem, we actually block the attack instead of just alerting user and telling user to do something with it. So in Tetragon, we block the attack, and we just tell the user that, hey, we blocked it. And this is difficult. This is difficult because there are very many things that are tempting to do, like send some event and then from user space and kill the process, whatever. These things don't provide a good security model because they rely on us trusting user memory, and we don't want to do this. So enforcement in Tetragon is done entirely in kernel, and this is also a thing where we have to be careful when we integrate with things like Kubernetes, because Kubernetes is distributed system. Kubernetes is designed to be run at a very large scale, but the enforcement bit happens in the kernel, and it can't rely on the whole entire Kubernetes system being in good state, because this very, very often isn't the case. In Kubernetes things go wrong all the time, and Kubernetes just deals with it. So the enforcement bit, we have to kind of separate this giant distributed system from the kernel, and this is why we, for example, get Kubernetes metadata not from Kubernetes API, but from something local from the container runtime. Okay, so now I wanted to show a little bit of Tetragon, like configuration and internals, how Tetragon is configured in Kubernetes. So how you can use it when you are not a kernel developer. Tetragon in Kubernetes is configured via tracing policy custom resource, which looks like this. Tracing policy, and we define which points we want to hook into. In this case, we hook into 3 kprobes: TCP connect, TCP close, TCP send message. So these are kprobes for opening, closing TCP connection and sending something over it. It looks like this. There is more configuration for filtering. So we can filter what events we want to get, for example, by Kubernetes metadata of the application. So for example, we want to monitor network activity only of this Tetra demo application in this case. And this configuration that I have over, this configuration that I have over here will be stored in a BPF map. And there are many other things that we can actually filter on than Kubernetes metadata. For example, we can essentially filter by like arguments of the kernel functions. And in this case, we filter by IPs. So this is example where we want to monitor only external traffic external to the cluster, connections external to the cluster. So here in the list, we put pod sider, services sider, and localhost. They will be ignored, and we'll get events for everything else. This sort of policy is very useful, for example, for air-gapped environment. We have some users like with high compliance air-gapped environment when they don't allow any external traffic, and then you can write a policy ad like this and alert if you see any event produced by it. Okay, so this was YAML, and just because I like showing C code on slides, I will now show how it's implemented. This is the only slide with C code, so there won't be more of it. But this is the actual BPF code for Tetragon implementing this IP filtering. It's very heavily truncated because to fit it on the slide, essentially. But this is the code. So I essentially get this get IP that is going on through the network stack. We do some map lookups here and here to check if this IP matches the configuration, which was previously stored in BPF maps, and then we return whether we should ignore it or not. All right. So I said a few slides earlier that I will show how to configure Tetragon if you are not a kernel developer, and this configuration, well, it didn't look like this, right? Like kind of to write something like this, you have to know what this function do exactly. You need to know that which argument in what function holds the IP address. Writing this requires solid kernel expertise, honestly. And so to make Tetragon accessible for the rest of the world, we develop sort of a policy library. So the Tetragon team has a few kernel engineers who actually write these policies a lot. I'm not one of them, but there are a few people who know all these kernel functions in deep details and can write the policies. And we have a policy library in Tetragon documentation. and also examples directory in the Tetragon repository. So the examples are sort of community maintained. There are many tons of different policies for different use cases. There are some policies for example, CVEs that you might have heard of. And the policy library in the documentation is sort of a curated list of policies that are recommended for some environments. This is you can just take policies from there and install them. All right. Advanced use cases, which we develop at Isovalent in the enterprise platform, are mainly in-kernel parsers for network protocols, which are also configured via tracing policy. So you just define which network protocol you want to observe and just enable it. You can also enable what telemetry data you want to get for this protocol. So for example, events or metrics or both. And you are just getting it. So all of this will enable some, we call them sensors, which are essentially like collections of eBPF programs that get loaded, and these programs are parsing some protocols, for example, HTTP DNS, and produce events for traffic for these protocols, so that we have, for example, not just IPs in TCP events, but DNS names of the destination, or we have all HTTP statistics like golden signals, so latency, errors, duration, HTTP, all metadata from HTTP. So this is what we are developing, and to make the setup easy, we also are developing the default rule set, which by default, I mean, it's recommended for most of the users, where it's essentially a set of policies for monitoring operating system integrity, for monitoring containers, some suspicious network activity, and to make it easy to install, we just put it in a Helm chart, and that you use to install Tetragon in Kubernetes, and with one Helm value, you can just enable this default rule set. All right. Oh, it worked this time. Dark side. So this was Tetragon configuration, and now Tetragon produces events. So far, I didn't say what an event is. I will say it now. Tetragon produces some telemetry data, which then is processed somehow in a data pipeline. There are a million ways of doing it. But one of a thing that we show in demos, for example, is Tetra CLI. So Tetragon comes with Tetra CLI, which you can use to query events. You run inside the Tetragon agent, you run Tetra get events, and you get, for example, these are events for the policy, the TCP policy I showed earlier. When we see the TCP connection opened, a TCP message sent with bytes count, and TCP closed. This is it. This is for demos. What is used in production more often is actually events in JSON format, and Tetragon events look like that. They are pretty wide JSON, where here we can see only part of it, but here we can see like process metadata. So Tetragon events are associated with a process, and for each process we can see all the Linux details of this process. So like what was the binary executed, its argument, process ID, start time, and also Kubernetes metadata. So in this case, this is event for Cilium pod running in copy system namespace. So we have these JSON events which are stored on disk or in a file. And this is pretty simple. This is super simple, actually. Like we just store JSON events in a file like a regular log. And this is what actually allowed us to run Tetragon at very large scale in high compliance environments while having very small team, just a few kernel developers doing this, because what you do with these files, with JSON events, is that you build a pipeline that is exporting them somewhere and then querying and visualizing these events, right? In Kubernetes world, this usually involves some logs collector, so something like FluentDiff, Wetbit, or OpenTelemetry collector, and then the events can be exported to any tool that collects logs, like regular application logs. So Grafana Loki is a popular one. More security-focused tools like Splunk or Elastic, and many people decide to build something on their own using, for example, ClickHouse or some AWS services. This thing is absolutely in no way specific to Tetragon, right? Like most applications do some logging in order to standard output to a file, but then there's a collector collecting logs, and then there's some storage. That's where you query and visualize the logs. Because we kept Tetragon that simple, that it just produces JSON events and stores it in a file, most users who have something like this already in place, which means any medium-sized or large organization can just reuse their pipeline and to process Tetragon events and do something with them. So this is what happens to events. Tetragon produces also metrics, Prometheus metrics. And this is how we do Prometheus metrics is a little bit different than most tools do it because we do eBPF, right? So we collect data in eBPF, aggregate them in eBPF, and store them in maps. How metrics are usually, how Prometheus metrics are work is that we collect the metrics, we expose them somewhere, and then Prometheus or some compatible tool scrapes them and then stores them, and then we query and visualize them, for example, using Grafana. These first two steps usually are one step we just call instrumentation, right? That we instrument application to collect and expose the metrics. But because we use eBPF and aggregate data in eBPF, we sort of separate these two steps. So the collection part happens in the kernel, and the Tetragon agent does only the exposing part. Tetragon agent reads metrics from eBPF map, and when Prometheus scrapes them, and just sends to Prometheus. And keeping it, this of course reduces the overhead, because we still we still have to store the metrics, just not in a user but in kernel memory. But but we kind of don't. We can store only what we need to. Okay. So now, how much time do I have left? Okay, 5 minutes, not much. Great. So I wanted to go quickly through some use cases, main use cases for Tetragon, and some. I will just go through some slides showing some visualizations that we work on. Our visualizations are mostly dashboards, either Grafana or Splunk, because we don't have dedicated UI team, and this is how you do UI. If you don't have dedicated UI team, you just do Grafana or Splunk. So yeah, this is what we do. So the first basic use case is the process lifecycle. This is the core of Tetragon. Tetragon monitors processes, and this allows us to find many interesting things about what is happening. So we can, for example, use Tetragon to monitor privileged workloads and processes. Nobody likes running privileged workloads, but sometimes you have to, and because you always do, you want to monitor if you are not running any additional privileged workloads. So this is Splunk query for it. Don't pay much attention to Splunk queries. I just put them on the slides. But we can just query for Linux capabilities, and we get this information. They take late process execution. So late process execution is when we start, for example, Kubernetes-native, it starts up, and usually we just expect it to run after this. Sometimes what happens is that after, an hour or so, something extra starts, some extra process in the pod. And this might be expected, but very often this is unexpected. This means that something went wrong, or the pod was attacked. So we can also use the process start time stored in Tetragon events to detect this. Malicious shell executions. This is something. Shell executions are also part of many security attacks, and we can monitor malicious shell executions in Kubernetes cluster using this binary stored in the Tetragon events. We developed dashboard for this. So this is Grafana dashboards showing malicious shell executions. And we kind of tried, this is, we are trying to take this out of the box approach where, you can just install the dashboard and it will work in all environments. It's not easy, but we are working on this out-of-the-box dashboards for example, for Linux capabilities and namespace changes. This is Splunk, not Grafana, but this is Splunk, like sort of audit dashboard that shows Linux capabilities and namespaces. Another use case is network visibility. So suspicious network activity is something, of course, every security team wants to monitor. We also developed these Grafana dashboards that can be used for many things. It can be used for security use cases, like as Tetragon was initially designed for, but these are actually also very, very useful for just monitoring network activity of the applications, because we have also bytes count, and also we can combine what we see on the network with, for example, files operations. This opens up really many interesting use cases when we can, for example, get very interesting information about what databases can do when we have all the bytes counts and all details about file operations. This provides very great insights into database operations. Yeah, so these are dashboards for, I think, TCP, latency, and throughput. And TLS compliance is another network-related thing that's very crucial to monitor for most security teams. So to detect weak TLS ciphers, weak TLS versions, malicious or new domain names, and things like self-signed certificates. So again, auditing things with such a dashboard is something that most security teams need to do. And data exfiltration. Something that we found out that many people are interested mostly in external traffic when when using Tetragon, because external traffic is usually associated with first higher cost, like requests to a SaaS platform or external requests are usually charged more by cloud providers, so they are associated with higher cost, and also they are subject to serious security attacks. A request to, for example, external payments platform or things like this. So so that data exfiltration is another example of this, where external traffic is something we monitoring, like the throughput to external URLs is something we are providing visibility to. And yeah, this is this dashboard shows us the external external traffic byte counts. File integrity monitoring is the last major use case. It's we also develop out of the box dashboard that provides visibility into operations on sensitive files. And we see here file operations. So read, writes, deletes, all of these file operations, and changes to passwords, for example. This is one of the main and sort of most obvious things we want to monitor when it comes to files, that nobody changes secrets that are stored on the disk. All right. So this was it to wrap up. To learn more, I put a few links here. If you want to learn more, then we have hands-on labs on Isovalent websites. There are not that many specifically for Tetragon. I think some of them are for Cilium, but there are some. So feel free to take a look and do the labs. They are pretty fun and I think efficient way to try out without installing Tetragon in your own environment. There is an O'Reilly report written by my colleague that you can download from the Isovalent website for free for the price of your email, I guess. So check it out too. And on the Isovalent blog, we have detailed walkthroughs through several of these use cases that I just quickly shown. So things like file integrity monitoring or specific CVEs that can be detected and blocked with Tetragon are covered there too. So check it out if you are interested in some specific use case and deep dive into it. Try it out. And if you are interested in contributing to Tetragon, then it's definitely more than welcome. By contributing, I don't mean only writing code, but also we welcome. It's very helpful when you try it out, experiment with Tetragon, and tell us about the bugs or difficulties you found out. Because Tetragon is such a low-level tool, it's sometimes sometimes it might scare people. So if you try it out and tell us what was easy and what difficult, this is super helpful. Tetragon repository is on GitHub under Cilium organization, Tetragon documentation and the Tetragon.io. In Tetragon documentation, you can also find walkthrough through a few of these use cases and the policy library too. And we have Slack. There is a Cilium and eBPF Slack, which you can register in, and there's Tetragon channel, so feel free to jump in and ask questions or share whatever you want to share. And in general, if you are interested in eBPF and want to connect with people using eBPF daily for many different things, then this is the right place to be. All right, this is it. Thank you very much.